Okay. Okay. So hello everyone. This is our last tutorial before the midterm exam, and we will gonna continue from the model stealing, second part for SSLs, and also the robustness. I hope that you have taken a look at the question sheets, and today we are gonna basically discuss those questions. So. We can start by laying foundations on different models that perform self-supervised learning for vision domains. And the three types of these self-supervised learning methods that you saw in the lectures were SIM-CLR, SIM-SIAM, and Dino. And so the first question was asking that to draw these computation diagrams of these different methods. It should be simple. We will go through the details for each of these methods, but there's a big distinction between each of these self-supervised learning methods, although they look similar, but their core functionalities may be different. So the core similarity between all these methods is that they all use the two different views or two different augmentations of the same given image. But these two different augmentations serve different purpose in each of these methods. And if we start with SIM-CLR, as you can see in the diagram, the same network receives input two different augmentations or two different views of the same image, and it passes through the base encoder, which in their paper mentioned that they use ResNet, different versions of it. And after that, it's passed through the base encoder. We use a projection head, which is a simple two-layer network. And yeah, and we use the contrastive loss in order to learn the network. So the goal, uh, the goal of this SimCLR is that we use contrastive loss. This means that we want to push the similar examples closer to each other while pulling away the unsimilar examples further from each other. So this is the based on the loss we have, the contrastive loss. This is the objective we are implicitly following when training the SimCLR and the self-supervised learning using the SimCLR. So yeah, the same network is used in the both branches, and only single loss is used to update the network. The other approach is SimSiam, and the difference is that we have a prediction head instead of this single projection. And basically, the objective here we are following is rather different from the SimCLR one. Here, the goal is to one tower of this architecture or one part of this network predict the representation of the other part. Whereas in the previous section, we saw that the goal is to push the similar examples closer together. And this is reflected in the loss we use. And if you can see, this is a definition of the cosine similarities, where we take dot product of the representation between two parts of the network. And we divide by the L2 norm of these, basically the vectors. Again, similar to SimCLR, the same network is used in the both of the branches. And the third method that we saw in the lecture was Dino. Here, there's a core difference between the this one and the previous two methods we saw. And here we have two models, a student model and the teacher model. And here our goal is to teach the student model to mimic the behavior of the teacher model. So in the previous examples, we had both branches using the same model. Here we have two different networks. with different parameters. It means they are initialized differently and updated differently. And as you notice that in the right-hand side branch, similar to SimCM, we have stop gradient operation. And the teacher gets updated using the exponential moving average of the student network's parameters. This means that the teacher network does not receive direct loss back propagation, and it's only updated via the parameters of the student model. And this is the core distinction between this Dino model and method and previous two methods that we discussed. Although remember that the SimCM method also uses the stop gradient in its network. So the question comes to our mind is that why do we use stop gradient in these networks? So I think the answer is apparent, but if you have any opinions, I would like to hear. So the problem we have in self-supervised learning is that it is possible that network learns a representation and maps all of the images to the same representation. This means that it only hacks the loss without learning any meaningful features. And this is known as the representation collapse. And the reason is that we use a stop gradient because it's because that we don't want to receive back propagation signals from the loss to the teacher in the case of Dino and other encoder network in case of SimCM to receive any loss back propagation from the given loss in order to prevent this representation collapse. And if you have noticed that we don't use such stop gradient in SimCLR, and any opinion why doesn't representation collapse happen in the SimCLR? Well, the point is that in SimCLR we have uh, negative and positive views of the data point in a batch size, in a batch which is passed to the model. The augmentation or the different views of the same input image are considered as a positive example in the batch, and all other examples existing in the batch are considered as a negative example. So this way, we have a clear distinction between the positive and negative examples. And in SimCLR specifically, the key to have a generalizable model is to use larger batch sizes, such that we have diverse set of positive and negative examples. Any questions up to this point? Yes, please. Yes, you have one positive example and the other examples are negative. And the other part of the question, I hope it's visible from here. I had to fit it into one slide. All self-supervised SSL algorithms we saw in the lectures were for the vision domain, but it's also interesting to see how these algorithms behave in the language domain. And the question asks you to provide the pseudocode for this self-supervised learning for the language domain. And it should be simple. As you remember, I think it was BERT, bidirectional. I don't remember exact formation, but I think, yeah, we had transformer that learned the representation of the text input, and we masked, let's say, P% of the tokens, which in the BERT paper they use 15%. And the task of this transformer encoder is to learn to predict those masked tokens. And basically, this pseudocode does the same thing. I think we don't need to go through the exact details of this pseudocode, but overall objective is the same as the BERT transformer encoder training process. You just mask out the random tokens, and the network's task would be to just predict the masked tokens given the input context. So, yes. Sorry, if you could a bit louder, I would appreciate it. It's a bit hard. Mhm. Yes, definitely. Definitely, it's possible. Specifically in the case of SimCLR, you are using only one example as positive, and the rest of the batch is negative examples. So it is highly possible that you might get very few signal from the positive examples. So you should adjust your batch sizes accordingly to prevent such cases. And also, if you go through the papers, I don't exactly remember, but there were other cases of happening the um, representation collapse. For example, in the case of Dino, I think if you remove each of these softmax or centering parts, they also cause the representation collapse. And even for the vision models, after a certain point, it became the over-engineering part where you have to add certain parts to the network or your method in order to make it work. And although they bring some motivation why they add such things, but if you remove those parts, such as centering or softmax, and they also make the representations unstable and also cause the representation collapse. Any questions? So the other question was about measuring the quality of the stolen model. So now that we have a stolen self-supervised learning model, we have to come up with a way to measure how similar or how good our stolen model is. And it's also useful for the case of research purposes where you want to measure the effectiveness of your method. And in the lecture slides, you were introduced into two methods. The first one was mutual information, and the other one was cosine similarity. Well, for the mutual information, is that we can interpret it this way. We want to measure how much information the stolen encoder's representation contains about the target encoder's representation. So we want to add up the entropies of these two representations, and we subtract the joint entropy in order to measure how much information this stolen representation contains about the target representation. And the interpretation for the cosine similarity is rather a geometric version, whereas the mutual information was information theoretic interpretation about measuring the amount of information contained in the stolen representation. And in this case, we want to measure how close these two representations are in one direction, and a higher value of this cosine similarity means that both representations are geometrically aligned, and they have the same direction. And if we consider both of these cases regarding the mutual information and cosine similarity, if both cases this means that we have a stolen representation or stolen encoder which contains more information, high amount of information about this target model, and the representation it has is aligned geometrically with respect to the target feature representation we have. This is the 2 points of view that we can have regarding the measuring the quality of the stolen encoder. Any questions up to this point? Yes, please.
Is it possible that one of them is high and the other one is low? What does it mean that?
Well, the both equations are not related in that sense that one gets high, the other one should be higher. What we have for the mutual information is the measure of how statistically dependent is this target, the stolen representation to the target representation, and the other one measures the direction. I assume it is possible to have representation is stolen, which contains a high amount of information where the directions might not match, but I'm not sure about this. So I may need to check, but I think these two definitions are somewhat orthogonal to each other. So now that we have seen multiple methods of stealing encoders, and also we measure how to we learn how to measure the quality of these encoders. And there was one question which gives you a hands-on experience how to deal with these defenses, which should be easy, but you need to know which basically obfuscations you can apply to these representations in order to perform a defense against the adversary. So here you can come up with shuffling as word in the lectures, and also adding a constant value, and also linear transformations. And the fourth would be that any combination of the given obfuscations would work in this case. So this should be a simple example. Just the goal was to introduce you different obfuscations that can be applied.
What application number two added constant value is just added to one of them.
And we have RD dimensional visual representations, which we add one constant value, which adds to R to the power of D plus one, which adds one dimension.
But for the other kind of obfuscations, for example, the third one, it is applied to all of the entities.
We add only as a new dimension. We add a new constant as a new dimension. I think it was the same way in the lectures. If you, yeah.
Like,
We can pass through this. So the problem with obfuscation, as you remember in the lectures, was that so you're hurting the benign utility in this case, since you are changing the representation that is going to be used also by the benign user. And this is the idea, this is the place where the idea of active defense comes into play. And the whole idea is to measure how differently adversarial user and benign users behave, and based on that, adjust the cost for each of these users without having to altering the representations. So it works on the motivation that we map the queries made by the each user, and we create a map of these queries in the representation space, and we measure how basically which fraction or what fraction of this representation space is covered by these input queries. And the research cited here shows that basically when adversary wants to steal a model, it needs higher generalization. So it will query in a way that to retrieve as much information as possible. This means that the adversary will have high coverage in the representation space. Whereas the benign user usually uses in a way for a downstream task. This means that the queries made by this benign user remains limited in a small fraction of this representation space. And this way we can differentiate between the benign user and adversarial user. And what is the goal here is that we design a puzzle which the user has to solve before receiving the answer to to their queries. And this difficulty for this query is adjusted based on the coverage made in the representation space. So here we don't alter the representation vectors. All we do is to increase the cost of the querying the model for the adversary. So any questions? Okay. Yes. Same. Um, well, the next question was to delve deeper into differences in the optimization algorithms used for the gradient descent in the case of stochastic gradient descent used for the updating the model parameters. And the other one was regarding the adversarial examples. And it's noteworthy to note the differences between these two equations. Um, in the case of stochastic gradient descent, as you notice that our goal is to update the model's parameters in a direction that is expected to decrease the loss. So our goal is to update our parameters in the direction of the steepest direction, which is given by the gradient of the loss with respect to the parameters, and subtract that value multiplied by the learning rate. However, in the case of adversarial example, instead of updating the model parameters, we use the gradients to update the input image or input data, or whatever we are using. So in this case, our goal is to increase the loss rather than decreasing it. So we have a small perturbation multiplied by the gradient, and we add the input image, and then using different algorithms like FGSM or PGD, we end up with having an adversarial example for the network. I think it should be trivial, but it's noteworthy that what is the reason we are increasing the loss here. Well, the main point is that we want to have an example where we pass the example as input to the model. We will have high loss. This means that prediction made by this by the model, given this example, would be the wrong version. So way to do this is to adjust the example in a way that it increases the loss. Okay. One of the methods you learned for crafting adversarial examples was fast gradient sign method, or FGSM. And the question asks, why do we take the... you have a question?
I have a question, but this is like that we are going to change the class of the predicted class, for example, and because of that, we are increasing the loss.
Yes. And the optimization process, if you have seen in the machine learning course, is that the canonical loss used for classification is 0-1 loss. And since 0-1 loss calculation, optimization is a hard problem, we use a surrogate loss. And here we are using the surrogate loss, whatever it is, in the hope that it will increase the 0-1 loss, which is the misclassification. And okay, in the case of FGSM, the question asks, why do we take the sign of the gradient rather than the gradient itself, which we lose the whole value of the gradient, and we only take the sign of it. The goal for this case is that we want to design L infinity bounded attack. So maybe this slide would make things clear. If you see that in the case of LP norm, we have the given equation inside the limit. And in the case of L infinity norm, we take the limit of P to the infinity. And if we solve this limit problem, we will end up with a maximum of absolute values of given vector. So when we bound this value into epsilon ball, as you can see in the figure on the right-hand side, is that let's consider an example where we want to add a perturbation given by this delta vector to a two-dimensional image, very simple case. And we want to bound this perturbation to epsilon unit ball in L infinity norm. In this case, the maximum variation value for each pixel independently will be equal to epsilon. However, if we use other cases like L2 norm or L1 norm, in this case, it was possible to get higher perturbation for a single pixel, whereas the other pixels received smaller perturbations. So the goal of using L infinity norm is that we want to bound the maximum amount of perturbations for each pixel independently to become to epsilon. And that's why we designed limited in the L epsilon, L infinity norm. And that's why we use the sign of the gradient rather than the whole vector of gradient instead. We want to design an attack which is bounded in L infinity norm.
What if they still take the sign and it's not
Sorry.
what if this I mean the design and it is not infinity bounded, is it a compulsion that it has to be infinity bounded and then only can we take the sign?
When you take the sign, the whole optimization problem becomes L infinity bounded. This means that you are not moving any pixel higher than epsilon value.
Have cases where we exceeded epsilon and then we took the epsilon as the final value, so that was L1 or L2 norm.
Yes, in the case of L1 and L2 norm, your overall perturbation is bounded to epsilon, but in the difference is that it is possible to get higher than epsilon for 1 pixel, which makes the attack more obvious to human eye specifically, and the other pixels become lower than epsilon. But in this case, you are bounding each pixel independently to become epsilon, such that the attack becomes less visible.
If it exceeds epsilon, we set it to epsilon.
In the case of other norms, right? No, you don't have to do it, since the overall vector norm is equal to epsilon.
So if it was exceeding the second, we were putting it back.
In the case of project gradient descent, I think, yes, this is a different method, and we are specifically discussing regarding the fast gradient sign method. Yes.
The robust and L-known attacks. Can we say that this is robust on L2 and L1 also?
As far as I remember, there was a figure with this regard.
Yes, okay.
I
So
think-
basically you have to train also from the L1 or L1 to the robust. So you get in this more robustness to train on human, but if you want more robustness, and basically you clip the gradients as we showed in the lecture if your optimization is for the LED node. So it can be FGSN, it can be HD, but this clipping actually was done for LED node.
Any questions? Okay, so the next question was regarding the min-max optimization, which is used for adversarial training. So any optimization problem of this form, where you are when you have an inner maximization problem and outer minimization problem, is known as a min-max optimization. So we now discuss the role of different parts of this min-max optimization. So as you notice, you are performing maximization. I think there's a mistake in the slides. This should be maximized with respect to delta. I will fix that after uploading. So we want to find the maximized perturbations such that it increases the loss. And then after finding this adversarial example, which increases the loss, we want to minimize or adjust the model parameters in a way that it minimizes the loss given input the perturbed image. So this is two-step process. First, we want to find the maximum possible perturbation given allowed set of perturbations. And then given the input data, we adjust the model parameters in a way that we minimize the loss. This is the role of the min-max optimization done by the adversarial training. And the question is that why such process improves the robustness of the model against the adversarial example. And the point is that here, when we are doing the adversarial training, we are not only training the model on the clean examples, rather we also have adversarial examples crafted during the optimization process, where the model sees such examples during the optimization, and it also learns how to correctly classify correct examples as well as the adversarial examples. And also, as you remember in the figure in the lecture notes, this adversarial training shifts the decision boundary to become away from the data points, such that the small perturbations of these data points prevents the model from having the adversarial examples or shifting the decision boundary. Also, adversarial training is one of the effective methods, but it also has side effects. And as you notice, we have a double optimization problem. And we have, in this case, a higher cost. This means that not only we are trying to update the model parameters, but also we need to craft these adversarial examples during the training process, depending on the method. And this increases the cost. And also we have accuracy trade-off. And if you have noticed in the results shown for the adversarial training, although we receive higher robust accuracy, but on the other hand, we see a trade-off for the clean accuracy, which will be dropped. And this is due to the shift we apply to the model's decision boundary. Sorry? Yes, yes, I will fix that equation. This is maximizing delta. Any questions? Yeah. And yes.
The bypass with respect to actually the channel stuff and cost for training, I think.
Sorry, I didn't get question.
Higher cost means that cost for training the model would be higher.
Yes, the whole process of the training will be higher since you are also crafting adversarial examples. There was one question regarding the capacity of the models and the behavior against the adversarial examples. We saw that the adversarial training requires the model to have higher capacity, since not only we want to correctly classify the correct examples, but also we want to correctly classify the adversarial examples, which requires higher capacity in terms of number of parameters. But in the figure also, we saw that we can see a diminishing result for increasing the model size. For example, from ResNet 18, ResNet 10 to ResNet 18, and also to other variants, we see a significant decrease in the robustness training error. On the other hand, when we move on from the ResNet 26 to other variants, we see a diminishing result. This means that the increasing the size or increasing the capacity of the model is not enough on its own to solve this adversarial example problem, although it can be helpful in the case of adversarial training, since it provides a higher capacity for the model. And also, as you can notice, the robustness case, we are dealing with a high dimensional optimization problem. And here we are involved with a higher level of stochasticity, and any other factors can also be impactful in the case of adversarial examples rather than only the model size. Since if you notice here, if you increase the model size from ResNet 10 to ResNet 26, you see a high gap between the two. But further increasing from ResNet 26 to ResNet 50, you see that drop in the error is not that significant compared to other ones. I think it's the last question. And here, the question is sourced from this paper, where we analyze the activations of the input network, a specific layer, which is the second to last layer of this classifier network. And we have two variants of the model, which is normally trained, shown by the left-hand side figure. And the other one is adversarial trained, the same figure as in the lecture slides. And we craft adversarial examples for each of these networks. And what we do is that we measure the activation threshold, and we measure the activations of this network in a specific layer. And if it passes a certain threshold, we consider it as active. And through different examples for a given class, we count the number of the activations for the given channel. And we then plot the frequency given the channel in a descending order. So the question was about how we can interpret this figure. So as you can see in the left-hand side figure, specifically in the left-hand side of that sub-figure, we can see that the natural examples activate a subset of these channels, specifically with the high frequency channels on the left-hand side. And you can see there's such shape. On the other hand, if we plot the same activation channels for the channel activations for the adversarial examples, we see a uniform behavior. And this is the case where the behavior on the adversarial example and the normal or natural example is different for a standardly trained model. So this gap could be an explanation for why our model performs poorly on these adversarial examples. On the other hand, if we do adversarial training, we see that this frequency of activations in the channels almost matches with the natural examples, although there still remains a gap between the two. So we do not perfectly fix the problem, but it perfectly shows that in the terms of frequency of activations in the network, the adversarial training could be helpful and beneficial. So these are the frequency given in the y-axis. And as we move further to left, we see higher frequency, showed higher values. And since it's descending order, we can see that the frequency drops as we move towards further to right. So the conclusion would be that the adversarial training improves the model's robustness, and we can also measure this robustness in terms of the model's internal activations. So through adversarial training, we see that the activations becomes consistent with the natural images or natural examples given the same model. Any questions? Yes, please.
Question regarding the metering that could you please explain about its type and how, I mean, that it's not conspicuous and it's like exactly it's the same as final exam?
Yes, it's the same thing. So basically, it's an open question exam type. So basically, we ask a question and you have to basically provide two sentences or one sentence regarding specific aspects. Also, there are questions that you have to conclude something.